study? So this time I'm giving the talk on my behalf. But the whole study was performed in collaboration with Sylvain and Pierre from Onera. And the main motivation initially was, okay, we can observe meteors only half of the day, so is there a way to observe them 24/7? And the starting point was that Rossano et al. From an airplane campaign measured, detected a few frames of meteors in the mid-infrared band, and their conclusion was that meteors emit 25 more times more energy in mid-infrared than in visible. I was like, wow, 25, that's a lot. But then the question is, how do meteors emit light exactly in mid-infrared band? Well, we didn't know. Another thing is that the sky brightness decreases with altitude. So suppose you put your camera in a stratospheric balloon, well, maybe there will come a point when the sky is so dark that you can actually observe meteors in broad daylight. So the question 2 is, how dark is the sky in mid-infrared band as a function of altitude? And the last one, can we detect them in broad daylight? And to answer that question, the way you do it is you compute a signal-to-noise ratio. Okay, how do meteors emit light in the mid-infrared? That's basically what we did in the wind tunnel. So this is taken from the presentation of last year. So the measurements were performed by Sylvain, and that's he basically showed that the spectrum of a meteor in mid-infrared, so mid-infrared, by the way, is from 3 to 5 microns. It's basically a black body at 2,000 Kelvin emission, 2,000 plus or minus 200. So that was 1 meteorite in the visible and the same in mid-infrared. Okay, so question 1. Okay, how dark is the sky in the mid-infrared band? So these are simulations performed by Pierre. So you have here the wavelength, and the visible is here, and infrared starts here up to there. Mid-infrared is from 3 to 5. So this is at night from the ground. So in the visible, it's extremely dark. Okay, that's 10 to the minus 3. It's a log scale. As soon as you go to mid-infrared, the sky is actually extremely bright. So forget about detecting meteors from the ground, even at night. Now, if you go at 20 kilometers of altitude at noon, it's a different story. In the visible, well, the sky is extremely bright, obviously. But then when you go around 3 microns, it's as dark as the sky at night in the visible. You have the same level here. So we can have high expectations. So the things that we wanted to compute the signal-to-noise ratio of a meteor observed from a camera on board a stratospheric balloon. So what we did is that we considered the same parameter as in the wind tunnel to start with something that we know best. So that's the characteristics of the feature of the mid-infrared instrument. That's 20 frames per second. And we can compute the readout and the dark noise. The target is quite a big one, 1 cubic centimeter, black body emission at 2000 K. And we will compute the whole thing for different geometry. We suppose the altitude of the meteor is 100 kilometers because that's a round number, meaning that it's not resolved by the camera. It's smaller than 1 pixel in the field of view. And then we compute the sky brightness and transmission for different altitude from 15 to 40, because that's the usual altitude of stratospheric balloons, like weather balloons. For azimuth, basically to the north, the west, and the south, because we expect that when we observe to the south at noon, the sun is going to have an influence. And for different elevation above the horizon, low above the horizon, and high above the horizon. And we do it in the winter and in the summer to have 2 extreme data. So we compute the sky transmission and luminance. That will be the noise, the background, and the meteorite luminance. And we convert all this into photoelectrons. And then we add the instrument signal, readout noise, dark sky meteors. And we convert all of that into tensions. And the signal ratio is the tension by the meteor signal divided by the sum of all the other signals. And by the way, I did not do the math. Sylvain did it for me. And what I did is that I converted all of that into Python code. Okay, here are the results. So that's the sky spectral luminance. This is a linear scale from 3 to 5 microns. So basically, between 3 and 4.1 something, there is apparently not much. And then there are emissions from the sky itself. And that's the transmission. So there are windows. The transmission is actually extremely good until, well, the same wavelength here. And that's the black body coming from the meteor. So the scale is 10 to the 18th and 10 to the 15th. So what's critical is everything that's happening here. And by the way, yes, this was computed for the winter at 20 kilometers of altitude, not looking towards the sun. So now if I do it and I compute the signal to noise over the whole band, and I do it for different azimuths here, basically the azimuth doesn't have a huge influence. What has a huge influence is going to be the elevation above the horizon. So that's 10 degrees, 30 degrees, 45, 80. So basically, the lower you observe, the worse the signal to noise ratio. And why is that? Well, because that's, the meteor emits like a black body. So the further away it is, the less signal you're going to get. So basically, you can have signal to noise ratio more than 1, this is even 2, under certain conditions, provided basically that you point your camera high up to make the physical distance between the camera and the meteor as small as possible. So this was computed for the winter, for the summer, and so on. And then I was thinking, well, maybe I can narrow down the whole band, because yes, 3 to 5 microns is good, but okay, there is sky emission here. So what if we restrict this band and so on? Maybe we can get some better signals to noise ratio. And I did not update those graphs, but yes, I can compute signal to noise ratio more than 2 in a restricted band. However, okay, this is 1, this is 1.2. So the conclusion is, yes, it's feasible, but it's really not easy. And the higher in the sky you are, the better. And of course, the shorter you're going to be at the high altitude. The driving factor is the physical distance, again, because it's a black body emission. The last thing is that we assume it's a point-like source, and when there's fragmentation, that might not be true. So we're still working on that. Unfortunately, I don't have high expectation, but stay tuned. Thank you.
Thank you, Jeremie. Any questions? Peter.
Thank you very much. Sounds interesting. What kind of camera do you use for this? First question, and then I have a remark to your when you presented the numbers of the exposure time.
So the kind of camera I need is the expensive one. So basically, mid-infrared cameras are used by the militaries to spot, like bombs and whatever from far away. So when I email some company, most of the time they don't answer me.
Okay.
And I contacted a French manufacturer, and he was like, "Do you have any idea how much it costs?" I was like, "I know it's a few tens of €1,000." He was like, "Yes. I expect between 50 and 100.
Yeah, okay.
So
yeah, well, that was a guess.
Yeah.
Okay, can you go to the exposure time or integration? Yeah, there.
Yeah.
Why do you use only 5 milliseconds when you have 20 frames per second?
5 milliseconds is how many frames per second?
No, you have 20 frames per second. Then you could use 50 milliseconds integration time.
Okay, that's my fault. I did not convert that number correctly, but the exposure time is 5 milliseconds.
5 milliseconds, but that's very short. Why?
Yeah. That's the setup of the camera when we observe in the wind tunnel. meaning that we can play with all of that, and the first thing I want to play with is the focal length, because 100 millimeters is not acceptable. Long story short, it's not over, and I'm currently playing with all the parameters. But you're right, this conversion is probably not correct.
Okay.
My
We will talk about that later. Thank you.
I would suggest that you will observe not the surface of the meteoroid in mid-infrared, but you should observe air emission, air plasma emission around the body. So it would not be the black body with 2000 Kelvin. It should be something other.
Okay, so my question is there a model that...
Yes, there are a few models, some hydrodynamical calculations with radiation transfer. The models are mainly elaborated for meteor-sized bodies. Maybe it's still applicable to meteorite class, meteorite production fireballs.
Okay, we need to talk. Thank you.
Yeah, sure.
Thank you very much. Okay, last talk for the session.